Welcome to this awareness briefing on managing invisible hazards in the workplace. I am your presenter, Pawan Singh. Should you need to follow up on the protocols discussed today, my direct line, 814-182-4876, is listed here. When you look across a typical industrial warehouse, the air usually looks completely clear. But if you magnify that empty space, you quickly realize workers are often standing inside a continuous storm of microscopic debris. This anatomical diagram illustrates why that debris is so dangerous. The primary route for toxins to enter the body is through inhalation. Because the lungs contain a massive surface area, they act as a rapid, direct gateway for airborne poisons to absorb straight into the bloodstream. A worker can set down a heavy tool or step away from a dangerous machine, but they cannot pause their breathing. Their respiratory system is constantly, involuntarily sampling whatever happens to be floating in the environment around them. Traditional workplace safety often focuses on the obvious. A falling steel beam or an unshielded gear demands immediate attention because the physical damage happens the moment an accident occurs. Airborne threats, however, operate entirely off the radar. This spectrum maps how hidden damage progresses. On the left, in alert red, is acute exposure, where high chemical concentrations cause immediate poisoning. Moving to the right, we hit chronic exposure. This damage develops slowly over years of low-level breathing. By the time a worker notices a chronic symptom, the internal lung tissue is already scarred. Ignoring these quiet, low-level hazards today guarantees irreversible respiratory disease decades down the line. To fight these contaminants, we must classify them. This infographic categorizes airborne hazards by size and physical state. On the far left, we have dust. These are solid, relatively macro particles generated by physical force, the high-energy breaking, crushing, and grinding of larger solid materials. Looking at these mechanical origins, we see the standard activities that generate this dust: heavy concrete drilling, masonry work, and demolition. These actions fracture materials at a microscopic level, releasing jagged silica and asbestos particles into the immediate air supply. Moving down to the microscopic scale, we encounter fumes. Fumes are frequently confused with gases, but they are clusters of microscopic, solid metallic spheres. They are born when extreme heat vaporizes a solid metal, and that vapor instantly condenses as it hits the cooler surrounding air. These thermal origins are entirely driven by high-heat industrial processes. Whenever a worker engages in welding, soldering, or high-temperature metal smelting, they act as the engine producing these toxic metal oxide clouds. Whether a microscopic threat is mechanically shattered into existence by a drill or thermally condensed from a welding arc dictates its exact physical properties. Knowing those properties is the crucial first step in designing a system to rip it out of the air. The final and most difficult category to trap is gas. This piping diagram tracks the common sources of fluid hazards, from chemical reaction vessels down to standard combustion exhaust. Because gases exist in a fluid state at room temperature, they are invisible and frequently lack any detectable odor. Their physical state causes them to naturally expand, aggressively filling every inch of available space. If a heavy gas leaks into a confined storage tank, it displaces the oxygen, turning a routine maintenance space into a lethal environment in minutes. To enforce safety, regulators establish the Occupational Exposure Limit, or OEL, defining the absolute maximum safe concentration. To measure those limits, we pull lab air samples for dust and equip workers with digital gas detectors to track exact individual daily exposures. Deploying these digital sensors removes the guesswork. Without hard, quantifiable data proving exactly what is floating in the air, any mitigation strategy you attempt to build is entirely blind. Once we have our data, we deploy a multi-layered defense to force concentration levels below the OEL. This hierarchy of control strategy is organized from the most effective structural solutions at the top down to the least effective methods at the bottom. Level 1 represents our strongest defense, engineering controls. This schematic demonstrates local exhaust ventilation. By physically modifying the workbench with heavy-duty vacuums and ducting, we extract the dangerous fumes directly at the source, long before they can rise into the operator's breathing zone. When it is impossible to fully engineer the hazard out, we step down to Level 2, administrative controls. This means restricting the time a worker spends in a high-risk zone, mandating strict housekeeping protocols, and restructuring workflows to limit dust generation. Notice the shift in reliability. An engineered exhaust hood physically changes the hazardous environment without asking anything of the worker. And administrative control relies entirely on human beings perfectly following the rules every single time. If the exhaust hoods fail and the rotation schedules are insufficient to drop the contamination below legal limits, we are forced to rely on the final, weakest layer of the safety pyramid, personal protective equipment. Looking at this progression of respiratory protection, you see the escalation in gear. But a respirator only works if three conditions are met. The filter must match the specific hazard, the mask must form an airtight seal, and the unit must be rigorously maintained. Maintaining this entire defensive architecture requires total cooperation. These interlocking gears illustrate the partnership. The employer maps the hazards and installs the expensive engineering controls, while the employee commits to following the standard operating procedures and properly wearing their assigned gear. At the end of the shift, the physics of airflow and chemical monitoring serve a single purpose: keeping a worker's biological systems functioning correctly. Protecting those lungs is the core moral obligation of modern industry, ensuring that everyone who clocks in leaves with their health and their future in